Hello, everyone, and thanks for joining us today. We are going to talk about viscosity, but not just a single number we often see on a data sheet. Then that one number is helpful, but it doesn't tell the whole story. Many materials behave differently depending on how they are handled or applied. So today we are going back to basics and looking at what is really going on beyond that single point viscosity. Okay, before we get into the details, just a quick introduction. My name is Soila Shabani-Berki. I am an application scientist at RealSense. I have experience in viscometry, rheology, and microrheology. I've been at RealSense for about 4 years now. During this time, I've been working with different materials, formulations, and fluids. So this topic, going beyond single point viscosity, comes from a lot of hands-on experience and practical challenges that we have seen across industries. So here is what we will cover today. First, a quick introduction to what viscosity is and why it's important. Then we will look at the problems with using single point viscosity and how it can lead to mistakes. Finally, we will talk about why multi-point viscosity gives us better insight with real examples to show how it works in practice. So let's get started. Before we dive into importance of multi-point viscosity, we first need to understand viscosity. Viscosity is the resistance of a fluid to flow. At the molecular level, it reflects the friction between fluid layers as they move past each other. So you can think of shear viscosity as a measure of molecular friction. It tells us about how molecules interact with each other depending on their size and shape. So in a way, viscosity gives us a window into the microstructure of the formulation. But it is important to know that viscosity is not just a single value. For example, viscosity may change with shear rate, which is the rate of deformation, the rate at which the fluid elements are deformed or sheared. So if we measure viscosity at just one shear rate, we only get a general idea and we cannot get a full understanding of the sample. To truly understand the formulation, we need to look at how viscosity changes, not just with shear rate, but also with temperature and other factors that can influence it. So let me walk you through a practical example of how relying on a single point viscosity measurement can lead to costly mistakes in biopharma, especially in mAb formulation development. Imagine you are developing a high concentration mAb that is meant to be injected. Most of us have had injections before, and we all know that those injections can sometimes be painful. In this case, a biopharma company developed a new mAb formulation and measured the viscosity at just 1 point, say 0.1 on this graph at very low shear rate. They calculated injection force based on this single value. But during an actual injection, the fluid experiences much higher shear rates as it's pushed through a small needle. And at those shear rates, those high shear rates, the viscosity actually drops because mAbs are shear thinning. So by only measuring viscosity at 0.1 or low shear rates, they overestimated the viscosity and therefore overestimated the injection force. As a result, they rejected a formulation that might have worked perfectly well in real-world conditions. Now let's flip the scenario. What if you only measure viscosity at like higher shear rates, say 0.2 on this graph, and ignore how the fluid behaves at lower shear? In this case, you could underestimate the injection force. And what happens then? So the device might not be optimized. The injection could be too slow, or it could be too forceful, and the patient might experience pain or discomfort. So this example clearly shows why a multi-point viscosity profile is essential. A single point viscosity measurement doesn't give you the full picture, and that can lead to wasted resources, rejected formulations, and even poor patient outcomes. To make informed decisions and develop optimized formulations, especially in injectable biologics, we need to understand how viscosity changes with shear rate. Okay, so now let's look at another real-world example, this time from the personal care industry. A company developed a new moisturizing lotion, and during product testing, they measured viscosity at just one condition: room temperature and low shear rate. The goal was to make sure that the lotion felt rich and creamy when applied, and the numbers looked good under those conditions. But once the product reached customers, especially in colder climates, a big problem showed up. The lotion became too thick to pump out of the bottle. Why did this happen? Because the company only looked at viscosity under one condition and didn't evaluate how it would behave across a range of temperatures or during actual use. So you know, when the lotion is squeezed or pumped, it can experience higher shear rates. As a result, customers complained and product returns increased. So the key takeaway here is simple. Ignoring how viscosity changes with temperature and shear rate can lead to poor user experience and costly product failure. Now let's briefly go over the limitations of other viscometers on the market that are still widely used in many labs, especially when it comes to measuring multi-point viscosity. Let's start with rotational rheometer first. These instruments are typically limited to low or moderate shear rates, so they can miss important behavior like shear pain in protein formulations. On top of that, they require large sample volumes, which can be a limiting factor if you are dealing with small sample volume and precious samples. These systems are open, and the handling process can be tricky with the risk of evaporation and interface effect that can lead to inconsistent results. And finally, they are not well suited for high throughput or routine QC. Measurements can take time and are often manual. Capillary viscometers are another common option, but they come with their own limitations. First, they only give you a single point viscosity value, which means you do not get any information about how the sample behaves at different shear rates. In fact, in these instruments, the shear rate is not clearly specified, and they are not based on first principle. There is no robust temperature control, so you miss how viscosity changes with temperature, which is critical for many of industrial applications. Like rotational systems, they often need large sample volumes, and the workflow is manual and slow. That makes them less practical for routine QC. So with that in mind, and now that we have seen the limitations of traditional viscometers, I would like to introduce a solution that overcomes all those challenges, the real-sense viscometer. This system uses a microfluidic flow channel, and here is how it works. As the fluid flows through the channel at a controlled flow rate, it creates a pressure drop due to the resistance of fluid. This pressure drop is measured with multiple pressure sensors along the channel and is directly related to shear stress. And using that, we can calculate the fluid's viscosity. This approach, this instrument allows us to measure viscosity across a wide range of shear rates thanks to the macrofluidic technology with excellent temperature control, small sample volumes, and a fully enclosed system, which eliminates issues like evaporation and interfacial artifacts. So with real-sense viscometer, we not only get accurate and repeatable viscosity data, but we also get a full viscosity profile that reflects real-world applications. Let's quickly look at how viscosity is actually calculated in the VROC system, and then we will continue with sharing the data and showing you how multi-point viscosity can help you understand the material better. So as we just discussed, the fluid flows through a microchannel at a known flow rate. From this, we can calculate the shear rate, which depends on flow rate and the geometry of the channel. At the same time, the system measures the pressure drop across the channel using the pressure sensors. So from the pressure drop and the geometry of the channel, we can calculate shear stress. Now that we have both shear rate and shear stress, viscosity is calculated simply by dividing shear stress by shear rate. One important thing to note is that the pressure drop should be linear to ensure high quality data, and we validate this with by checking the R-squared value of the linear fit. This R-squared should be equal or very close to 1. So when we talk about viscosity, it's important to remember that it's not just a fixed number, especially in real-world formulation. Viscosity is dynamic and it's influenced by different factors. Let's briefly overview these factors. First, shear rate. Many real-world fluids are non-Newtonian, meaning that their viscosity changes depending on how fast they are sheared or they are deformed. For instance, a lotion may feel thick at rest, but as you rub between your hands or pump it, the viscosity drops. That's shear thinning behavior. The second factor is temperature. Temperature can affect viscosity in different ways. You can have a sol-gel transition where a liquid turns into a gel as temperature drops. This can significantly change the viscosity. Or in protein-based formulations, high temperature can cause unfolding or degradation of protein structure that again can change the viscosity. The third factor is time. Some materials exhibit time-dependent viscosity changes even at constant shear and temperature. This could be due to thixotropy, structural reorganization, or enzymatic degradation, all of which may cause viscosity to decrease or increase gradually over time. And finally, molecular structure. This is where intrinsic viscosity comes into play. The size, shape, and interactions of molecules, mostly in polymers or protein therapeutics, all affect viscosity. Even two formulations with the same concentration can behave very differently based on molecular structure. So when we measure or think about viscosity, we need to go beyond a single point. In the next few slides, you will see real examples of how each of these factors can affect viscosity and why they matter in practice. For the first case study, let's take a look at how viscosity changes with shear rate using high concentration MAP formulations as an example. We know that other materials like polymers and colloids, emulsions may show shear thinning behavior, but here we want to focus on MAP formulation. Because high concentration MAPs are becoming more common, especially for self-injection. So on the left, you see viscosity versus shear rate curves for 10 different MAP solutions. What is clear is that most of them show shear thinning behavior, meaning viscosity drops as shear rate increases. One interesting question here is that why proteins shear thin? The right graph shows a typical shear thinning behavior. The viscosity starts out flat at low shear rates, forming what we call a Newtonian plateau, and then decreases as shear rate increases. This is the shear thinning characteristic. To explain shear thinning in proteins, we think of the protein molecules like colloidal particles suspended in solution. At low shear rates, the system is dominated by Brownian motion, so the movement of the molecules and the proteins is random and thermal driven. This keeps the system in a stable equilibrium state, so the viscosity remains constant. But as the shear rate increases, the hydrodynamic forces begin to dominate the thermodynamic forces or Brownian forces. These forces push the protein particles or clusters out of their equilibrium arrangement and cause them to align or deform in the direction of flow. So this is the shear thin. This actually explains why proteins shear thin and explains the shear thinning behavior of protein formulation. As a result, the system transitions to from Newtonian to non-Newtonian behavior, and viscosity begins to decrease. This shear thinning characteristic is typical in concentrated protein solutions, and that's exactly why it's important to look at viscosity across different shear rates, not just at a single point, because it makes a big difference in injectability that I will discuss in the next slide. With that in mind, let's see how it affects injectability. You know, viscosity can be used as a tool to predict injection force of a therapeutic. As we discussed earlier, to predict injection force, we need the full viscosity shear rate profile, not just one number. We have seen how relying on single point viscosity can lead to overestimating or underestimating injection force, both of which can cause serious issues in formulation or patient experience. Here, we are comparing injection force measured using two methods, the Instron measurement and the VROC-based analysis. With VROC, we can analyze injection force using either a single point viscosity or full viscosity shear rate profile approach. The key difference is in single point or Newtonian analysis, we only use the viscosity at the Newtonian plateau, essentially assuming viscosity is constant. But in non-Newtonian analysis, we use the full viscosity shear rate profile, including the shear thinning region. Now let's see the difference by looking at numbers. As shown in this graph, on the graph on the right, Newtonian analysis tends to overestimate the injection force, as indicated by these blue bars. In contrast, the non-Newtonian analysis, shown by green bars on the graph, aligns very closely with the Instron measurements. So we see that it gives us a much more accurate result. So I want to emphasize again, to accurately predict injection force, especially for shear thinning formulations, we must measure viscosity over a wide range of shear rates. A single point viscosity measurement does not give you an accurate value for injection force. Now let's look at the next case study and see how viscosity of protein changes with temperature and how this can help us detect protein denaturation in solution. Typically, simple solutions like buffer show a smooth, predictable decrease in viscosity as temperature goes up, something we call Arrhenius behavior. But with protein formulation, the story is different. In this case, we measured viscosity for 2 samples as temperature increased. One was a 30 mg per ml BSA, bovine serum albumin solution. The other was just the buffer alone. Initially, both samples followed the same trend. Viscosity decreased gradually with temperature as expected. But at around 60 degrees Celsius, the BSA solution showed an abrupt deviation from the buffer viscosity. This sharp change in viscosity is a sign of protein denaturation. It indicates that the BSA is losing its higher order structure that leads to unfolding and beginning to aggregate or associate. In contrast, the buffer alone showed no such deviation, and it continues along the expected Arrhenius curve. This clearly shows that the viscosity change is due to the protein denaturation and confirms that we can use this method to detect structural changes in protein. In addition, our viscometers are closed system, which helps avoid interfacial artifacts that can affect open systems like rotational cone and plate rheometers. For example, BSA is known to form gels at the air-liquid interface, but with VROP technology, there is no air exposure, so this issue doesn't occur. But in open system, it may occur and influence viscosity. All right, another interesting example of viscosity versus temperature is understanding thermal transitions or sol-gel transitions in materials. Let's look at kappa-carrageenan system, a polysaccharide widely used in food and pharmaceutical applications for its gelation properties. What we are showing here is a graph of viscosity versus temperature for 2 concentrations of kappa-carrageenan. At high temperatures, this material is in the sol or liquid state, where the polymer chains are in a random coil conformation, and the viscosity is relatively low. As the temperature decreases, the molecules begin to undergo a coil to helix transition, eventually leading to the formation of a gel network. This transition is marked by a sharp increase in viscosity as the material shifts from a flowing liquid to a gel. This behavior is non-Arrhenius behavior, and here we see a sudden jump as the gel forms. What is especially interesting is that this transition is fully reversible. If we hit the system again, the gel melts back into liquid. And also the exact shape and sharpness of this transition depend on several factors, like concentration of kappa-carrageenan, and also the type and the concentration of salt that's present in the system. because this system is ion sensitive. Here we added KCl or potassium chloride to the system. So by monitoring viscosity across the temperature range, we can clearly capture this salt-gel transition that cannot be captured with single point viscosity. In this final case study, we are looking at how viscosity changes over time during enzymatic degradation. Specifically, we are focusing on the enzymatic degradation of hyaluronic acid. The graph shows two samples. One is pure hyaluronic acid solution without enzyme. The other has hyaluronidase enzyme added. As you can see, the sample without the enzyme remains stable. The viscosity stays constant at around 11 centipoise throughout the 3-hour period. But in the sample with hyaluronidase, we see an exponential drop in viscosity falling from something about 8.5 centipoise to around 2 centipoise over 3 hours. This drop indicates that the hyaluronic acid polymer chains are being enzymatically broken down, reducing the molecular weight and in turn lowering the viscosity. This example is a clear demonstration of how viscosity can be used as a real-time indicator of polymer degradation, in this case triggered by an enzyme. This type of measurements is especially useful for studying formulation stability, controlled degradation, or even enzyme kinetics in different applications. Again, I want to emphasize that single point viscosity is not sufficient for capturing degradation kinetics. Okay, so let's do a quick recap. Today, we looked at why relying on a single point viscosity measurement can be misleading and how using a multi-point viscosity profile gives us a much clearer, more accurate picture, especially in real-world applications. We walked through several examples where this approach is essential. Of course, there are many more applications we could explore where multi-point viscosity plays a critical role, but we simply don't have time to cover them all today. That's why we are planning a part 2 of this topic, where we will go deeper into more case studies and cover additional industries and use cases. So stay tuned, and we hope to see you in the next session. Also, if you are curious about how your samples really behave under different conditions, you can send them to us. We will test them and help you see and understand the full picture beyond just a single point viscosity. Okay, thank you for attending today's webinar. And now we have a Q&A session. If you have any questions, please feel free to type them in the question box. I will do my best to answer them. Okay, the first question is that if my CRO is giving me one number, what do you recommend I approach so that they are giving me a full range of measurements? So if your CRO is giving you one number, first thing is to get the details of the conditions that they measured your sample. For sure, you need to ask about the shear rates that they test your sample at, the temperature, and after getting those information, you will see that if they measured your sample, for example, over a wide range of shear rates or temperature. So if they are giving you one number, for sure you should check with them to see what was the condition of the measurement, and if it's not like the full viscosity profile, you may ask to ask them to do the full measurement to give you a full picture of the sample. What's the particle limit for the chip options? Okay, so since our technology uses a microfluidic channel, the particle size can be a limiting factor, but still, if the particle size is 1/10 of the channel depth, you can measure the viscosity with our technology, because we offer different channel sizes, different channel depth from 20 micron all the way to 300 microns. So still, we can measure samples with particles as long as the particle size is less than 1/10 of channel depth. So can you go back to the slide of the cone and plate pieces for rheometer and explain the differences, also the difference between rheometer and viscometer? So let me go back to that slide. Okay, so the main difference between VROC technology and cone and plate. So unfortunately, I don't have data, but we have a published data on protein sample with cone and plate showing that the samples that are measured with cone and plate shows artificial shear thinning at the very low shear rates. So I showed here in this webinar that MABs are shear thinning, right? But at low shear rate, the viscosity is constant. There is no shear thinning at low shear rate. But as you increase shear rate, you will see the shear thinning behavior. Let me, maybe I can go to that slide to show you the graph here. So we see that at low shear rates, we do not have any shear thinning. Viscosity is constant. But as you increase the shear rate, this shear thinning characteristics starts to appear. So, but in cone and plate measurement with protein sample, it will show the shear thinning from the beginning. So from the very low shear rate. That's because of that's artificial shear thinning. That's because of the interfacial artifact. Because the sample can migrate toward the interface, and it shows artificial shear thinning. That shear thinning is not real. So this is one of the main limitations of cone and plate viscometers or rheometers for measuring protein samples. And also the difference between viscometer and rheometer. So rheometers actually can give you more information about like G prime, G double prime properties of the sample, the oscillatory properties, because in those instruments you can apply oscillatory deformation to the material. But in viscometer, for example, in VROC system, we just apply shear deformation to the sample, and we can just measure viscosity and not G prime, G double prime. So that's the difference between rheometer and viscometer. So when Real-Sense provides sample testing services and I don't know where to ask for shear rates or parameters, would you be able to help guide based on seeing the samples? Sure. So what we do here is when we receive sample testing requests, we get more information, especially about the application of the sample. So where the sample is going to be used and at under what conditions. So for example, if sample in the real world condition is going to experience high shear rates, we offer or we recommend our customers to measure the samples at higher shear rates. So we, for sure, we can help guide you on this and the sample testing conditions. Could you explain more about the graph related to protein denaturation? So let me go back to that slide. Yeah, in proteins, they denature or they can degrade at higher temperatures because, as you can see in this image, the normal protein is like this. So we have a higher order structure like primary, secondary protein, right? But as you increase the temperature, unfolding can happen like this. And these unfolded protein molecules can aggregate and they can form some sort of aggregation and clusters that can increase the protein viscosity. So this way we can actually study the stability of proteins. So for example, in the case of BSA, we see that over like 60 degrees Celsius, the BSA is unstable. So the real world condition for this protein shouldn't actually reach this temperature. Otherwise, it can be denatured, it can be degraded, and the viscosity can change. And I think it's not in a good like form to be used in real world application. Okay, let me see if we have more questions. I will give a few more minutes to see if you have more questions. So there's another question. What's the coolest application you have experienced when you measure viscosity? Actually, we have measured like a wide range of samples, and to me, the coolest one, for example, the salt gel transition that I showed you, it was actually interesting to me. That we could detect this transition with viscosity measurement. And also, for example, the kinetic of gelation, we did some experiments on gelatin because gelatin also formed gel at lower temperature, but it is time dependent. So we could measure that kinetic the kinetic observation with viscosity measurement. Another cool application is for example, again, denaturation of proteins, stability testing, stability measurement of proteins is another cool application. Yeah, these are the coolest applications that I can think of right now. Okay, I think so. I do not see any other questions. So thank you. I would like to end it today. Okay, now I see another question. Sorry, it is out of the topic related to yield stress. Have you experienced static and dynamic yield stress with this? So actually, with our system, we cannot measure yield stress. So there might be, in some of the samples, they might experience yield stress, but with our system, we cannot measure or monitor yield stress. Okay, I would end it today. Thank you again for joining the webinar. You will receive the recording in the next few days. Again, if you have any questions, you can reach out to us and we will be happy to help you. Thank you so much and have a good day.